Okay, so to conclude all this fancy stuff about creating a PDA, I'd just like to sort of tie this back all together with the actual mapping reduction. Because remember, what we're actually doing is a mapping reduction from the not halting problem to all CF, right? And so if you're asking yourself, what's the point of all this nonsense? What's the point? Well, it's now we know essentially we've shown that the PDA P accepts, right, L5 complement. And so this implies that L5 complement is context-free. And so that also means that there's a context-free grammar G that generates it because PDAs and CFGs equivalent computational power. So there's a conversion algorithm between them. Okay. And so what that tells me is that there is a context-free grammar G such that L of G generates, well, I know that I can generate L1 complement all the way to L4 complement because those are just regular languages. But now what this final result shows is that I can also generate L5 complement. And so altogether, I can create context-free grammar, which generates Valcomps MX whole complement. And that's great. Why is that great? Because that means that now given a instance of the not halting problem, MX, we can, right, so we can create a CFG G such that it generates Valcomps whole complement and check using the all-CF solver and check using the all-CF solver that Valcomps complement is equal to delta star, or in other words, Valcomps is equal to the empty set. And so then if the answer is yes, then that means that M loops on X. If the answer is no, then that means that M halts on X, right? And so this acts really effectively, this acts as an not HP solver, but because not HP is undecidable, this implies that all CF is undecidable. And so now I am much happier and much more satisfied with this box that I can finally put down. The box that I had put down during the lecture was less satisfactory. Okay. And so this shows that all CF is undecidable. All CF is undecidable. A good question to ask ourselves immediately is it actually even CE or co-CE? So it could either be either one or neither, right? It can't be both, because if it were both by Post theorem, that would mean that all CF was decidable. So let's see, let's think about it. CE means that if the answer is yes, then you can check it. Well, if the answer is yes, that means that L of G is equal to the universal of all strings. Well, how do you check that? You run through all the strings. That's an infinite loop. That's never going to end. But if the answer is no, right, that means that L of G is not equal to the set of all strings, right? So if the answer to all CF is no, then there exists some string in, let's say, so suppose I have G is VSTP, T is the set of terminals, so I have some string T in sigma star such that W is not in L of G. Well, now, if I do run a for loop, starting in lexicographic order from, the empty string, and I check if that string is generated by G using the CYKS algorithm, and because the CYKS algorithm always halts in a finite number of steps, right, then at some point, if I know a priori that W is not an L of G, then at some point I'm going to get that the CYKS algorithm is going to say no, and then at that point I can accept, right? And so that tells me that I can verify a no instance, right? So if I know this is true a priori, I know this is true a priori, I can check or verify. Okay. How? Well, let's just run a for loop. So for W and T star, do the following. So run the CYK, this should really be the CYKS algorithm on what? G and W. And so the CYKS algorithm finishes in a finite number of steps, regardless of what G and regardless of what W is, right? Because checking if a string is in G is decidable, right? So that means that for any grammar and for any input string, you're able to decide it in a finite number of steps. So this halts and gives a yes or no answer in a finite number of steps. And so if the CYKS algorithm says no, then that's the verification, right? That's the verification that the grammar doesn't generate everything, right? It doesn't generate all the strings. So if CYKS says no, then really what you should do is you should accept, because that's a verification. If it doesn't, right? If it says yes, meaning that W is in that language generated by that grammar, then you just move on to the next string, right? And so if L of G does generate all of T star, then this is just going to run forever. And that's fine, right? Because you don't care if the answer is yes. If something is co-CE, all you need to do is check that if the answer is no, you can verify that it's no, right? And so that means that all CF is co-CE, right? So it's undecidable, but co-CE. Okay, great. And so this concludes the bulk of the lecture about undecidable problems about context-free languages. I will do another video about the intersect decision problem. Excuse me. And I'll also show an example of how we can actually use the all CF problem to show that another problem is undecidable, and that's going to be helpful for your assignment.